morning session 11 for this. Sorry. Welcome to session 11 for the 5th International Student Science Congress. And today we will have presentations about civil engineering and especially from the structural engineering. My name is Selçuk Saatçi. I am from İzmir Institute of Technology and from the Department of Civil Engineering. In this, and I will host this session for you. We will have 5 presentations today in this session, and we will start with Ms. Ornella Lalaş-Şen about the sectional ductility of wide beams. Before we begin, I would like each presenter to introduce himself or herself with a few sentences. What are you studying? How did you come to Turkey? For how long have you been in Turkey? So it will be also nice to introduce yourself. Ms. Lalaş, you may start.
Hello, Professor. Thank you very much.
Professor Saatçi, I'm interrupting, please. Before beginning the session, I want to thank you for your contributions to our Congress, and I wish success to all of our participants and my student Ornella also.
Thank you, Professor.
Okay, thank you very much for this very nice organization and for this for all your efforts in this for this conference. Thank you very much. Okay, Ornella, the microphone is on you.
Okay, then. Thank you very much. Thank you for the very good, nice organization that has been going on for years now, and thank you for your presentation, Professor Selçuk. My name is Ornella. I'm a PhD student in İzmir in civil engineering, focused in reinforced concrete structures. I came to Turkey about 7 years ago for to study PhD, and hope I am in the end of my studies. I'm writing and will be soon, hopefully, be defending my PhD thesis, thus finishing my PhD. The topic today is a part of my a part of the studies that I have done within my PhD thesis, and it focuses on sectional ductility of wide beams. I can share this. Start sharing the screen. Okay, I cannot. I cannot share screen for now. The host needs to give me permission to do that.
Do you need to be host or?
It says that the host has disabled participant screen sharing.
Tamam, şimdi yapabilirsiniz.
How am I going to? Okay, thank you.
This is this study is about the sectional ductility of wide beams. Wide beams being the main focus of my PhD thesis. So, wide and shallow beams are reinforced concrete beams that have limited depth, which is generally compensated by greater width that normal beams do have, and also they are accompanied by greater reinforcement ratios, longitudinal reinforcement ratios as well, to provide the necessary moments due to the reduction of the lever arm. For these reasons, it is often thought that wide beams have limited sectional rotational ductility. Now, since in my thesis we have designed and analyzed a large number of wide beam frames, and we had a very considerable database of beam sections, we decided to to investigate the data for the beam sections that we already had in our hand to study their ductility behavior. We investigated ductility in relation with parameters that are thought to affect ductility, such as the longitudinal and transverse reinforcement ratio, and also with respect to aspect ratio, because aspect ratio is one of the most direct parameters which we can relate to a beam being either wide or normal beam. So we know that ductility is the ratio of maximum to yield displacement, and normally ductility is obtained experimentally from testing full-scale members and obtaining their moment, their force displacement behaviors, and then do this calculation. But there are a considerable amount of softwares that work on FE principle, which can also help to evaluate that the force deformation relationships. We used one of these programs, Extract, to obtain the moment rotation relationships of the beam sections. We modeled and we measured these beam sections. It is an FE program for member sections. We used Mender model to model confined concrete, and we used strain hardening model for steel, and then we obtained the relationships that we wanted. Regarding to the data pool of the beam sections, we had some fixed properties. Mostly the material properties did not change. We used C30 for concrete and B420 for steel, and some of the properties were varying. So we had two types of beam depths. Normal wide beams had beam depth of 300 millimeters, and normal beams had a beam depth of 500 millimeters. The aspect ratio, which we defined as width divided by depth, varied from 0.5 to 2.33, and the reinforcement ratios also varied from design, from the loading. So in here we have schematically shown the normal and the wide beams. Our normal beams all had a section of 250 by 500, while the wide beams had a depth of 300 and the width varied from 300 to 700 millimeters. All these beams were designed in accordance with the Turkish standards. The normal beams were designed as high ductility class, and the wide beams were designed as limited ductility class. As I mentioned, these beams were obtained from full frame design study. So they were designed for different load combinations, and different reinforcement ratios were, different moment capacities were obtained for each of these. Before starting investigating the ductility, we wanted to observe the reinforcement ratios versus the aspect ratio. As I mentioned, the aspect ratio is the one parameter that we can directly correlate to the beam being either wide or normal. So all the normal beams, as we can see here, have an aspect ratio of 0.5, and the rest of the aspect ratio values indicate that they are wide beams. And if we observe the relationship of aspect ratio with the top and bottom reinforcement for the beams, longitudinal reinforcement, we see that generally normal beams, the ones with the aspect ratio of 0.5, have lower reinforcement ratios, while wide beams have higher reinforcement ratios. This is something that we already expected. This is not this is not a conclusion of our study, but it is just an observation. When it comes to the transverse reinforcement ratios, in some cases, wide beams had same or greater transverse reinforcement ratio than the normal beams, and in some cases that they had a lower transverse reinforcement ratios. Now, the parameter that we expected to have the greatest effect on ductility was the aspect ratio, and also this was the one parameter that we could make the most, we could draw the strongest conclusion if we were to find relationships. However, I'm sorry. I'm sorry. However, from these graphs, we have here the positive and the negative ductility. The beams had non-symmetric sections, so we calculated the moment curvature relationships in both in the positive and negative directions. So we obtained two positive and negative ductility values. So we can see here that there is no clear relationship. So there is the values of ductility oscillate around 30. There is this range of 25 to 35 where most of the ductility values are, let's say, concentrated, but there are also outlier values as low as 20 or even lower and as high as almost 37. So from the aspect ratio versus sectional ductility, we were not able to define a clear correlation between these two parameters. And similarly, when we obtained the relationship between the ductility and the reinforcement, we were not able to observe any clear correlation. For lower reinforcement ratios, there was quite a scatter, as we can see here in the data points, and the scatter became less when higher reinforcement ratios were present, but there was no clear correlation that we could obtain. Similarly, again, for the transverse reinforcement ratios, there was quite a scatter and no clear trend at all. For example, in the reinforcement ratios, there was some sort of trend, a bit of convergence, but in the transverse reinforcement ratio, this was not observed. So we thought, okay, none of these parameters alone seems to have a clear correlation with the ductility. And we also observed that the ductility values seem to range in a certain data interval, value interval. So we thought that ductilities maybe could be observed as a distribution. So we plotted the histograms of positive and negative ductility values, and we can see that the histograms have quite a bell curve shape, especially the positive ductility, and a bit of a skewed bell curve shape in the negative ductility. So the ductility values for the beams are more of a normal distribution. And also, if we observe the mean values of ductility, both for all the beams and for normal and wide beams in separate data sets, we observed that the mean values were very similar for the positive ductility and also quite close for the negative ductility, and variance was very small as a matter of fact. So if we come to wrap up the study that we did, we had a database of 150 beams, which was, or more than 150 beams, that was investigated to draw relationships between, if possible, section parameters and ductility that was obtained numerically. And all the beams were co-designed. Normal beams were high ductility and wide beams were limited ductility. But we were not able to find a clear correlation between the ductility and the aspect ratio and ductility and reinforcement ratios. We observed that there was a ductility range between 25 and 35 mostly. So we thought that ductility could be more treated like a distribution, and this was also supported by the fact that the mean values of ductility were very similar for wide beams and normal beams. Therefore, while we were not able to find a correlation between the parameters, probably because the correlation is much more complex than ductility versus one simple parameter, we observed that all types of beams displayed similar levels of rotational ductility, even though they were designed, the normal beams as high ductility and the wide beams as limited ductility. And we could conclude that the most important factor affecting the ductility of these sections is the adequate design procedures, rather than the type of section, whether it is deep or that is normal, or shallow beam. So this is what we could conclude from our study, from the data set of 150 something beam sections. Thank you very much. This was my presentation. If you have any question, or if I went fast on something or anything, I could explain again, or I could answer your questions.
Okay. Do we have any questions from the audience? Well, thank you, Ms. Lalaj. That was a very nice presentation, actually. I had the chance to be in Ms. Lalaj's PhD committee, and it's a very nice work. And thank you very much. It was a nice presentation.
Thank you very much for your words, Professor.
Okay. And so if we don't have any questions from the audience, we can move on to our next presentation by Mr. Ehsan. And he will present us about the numerical analysis of flush and plate beam to column connection using mathematical model and finite element model. Mr. Ehsan, if you can introduce yourself with a couple of words at the beginning, and then we will be pleased to hear you about your presentation.
Hello, everyone. You have my sound?
Yes, yes.
Hello, everyone. My name is Mohammed Harun Ehsan. I am from Afghanistan, and I am the master student in Khatib University in Civil Engineering Department. And I'm in Turkey since 2017. And my topic is, let me share the presentation. Yeah. Yeah. The title of topic is the numerical analysis of flash and plate beam to column connection using mathematical model and finite element analysis. In the analysis and design of steel structures, beam to column connections are generally assumed as entirely rigid or perfectly pinned. This assumption simplifies analysis and design steps and referred extensively in structural engineering practice. However, experimental studies conducted in recent years have revealed that handling some of the beam column connection as entirely rigid and perfectly pinned does not give the realistic result. In fact, most of the connections used in current practice have some certain amount of stiffness which fall between the extreme cases of entirely rigid and perfectly pinned. In order to model the beam to column connection properly, several researchers have proposed various mathematical models based on experimental results. In these models, moment rotation relation of beam to column connections are defined according to the type of the connection. In this study, the moment rotation behavior of beam to column connection formed by flash and plate are investigated using finite element analysis and a well-known practical mathematical model. Moreover, the numerical analysis outcomes were compared with the test results of a reference study from the literature. These papers, also this paper showed the importance of structural design parameters in determining moment rotation relationship of flash and plate types of beam to column connection and evaluated the efficiency of the practical numerical models. The end plates are widely used in steel structure, which consists of two main types, extended end plate and the flash end plate. The various analytical and numerical methods have been developed to study of the semi-rigid characteristics of beam to column joints, as well as their influence of the response of the structural elements. In order to predict the moment rotation behavior accurately, a large number of studies have been performed on end plate voltage joints considering experimental, numerical, and analytical approaches. The types and details of the studied connections are numerous and innovative, and they concern many parameters such as diameter and number of bolts, pretension force of bolts, thickness of end plate, beam and column dimensions, steel yield strength, stiffening type, and coefficient of frictions between the contact surfaces. The first finite element analysis of the end plate connections have been performed by Krishnamurthy Tarpe and Cardinal carried out an elastic finite element study of unstiffened end-plate connection that was verified experimentally, and they also proposed a design methodology for these joints. Maxwell also developed a prediction equation for the ultimate moment of connections, as well as their moment rotation relations based on finite element analysis and on tests. Jenkins also did the finite element analysis on flash and bullet connections, and those extended on one side, then put forward a bilinear method model for flash and bullet connections. Cucretti adopted two-dimensional finite element analysis model to calculate 50 flash and bullet connections and verified the recommended moment rotation relationship for this type of connection based on regression analysis. Sherborne and Bahari used two-dimensional and then three-dimensional finite analysis models to model end plate connections. Also, Ade indicated that the presence of stiffeners on the extended part of the end plate increased the flexural strength of the connections, as well as its rotation and its energy dissipation capacity. The flash and plate beam to column connection model. Flash and plate beam to column connection are selected from a reference study of Ostrander. In the reference, geometric and structural properties of flash and plate beam to column connections were given in details, and laboratory test results were presented in terms of moment rotation relationship. The test setup of Ostrander includes two beam segments with equal lengths, as you see in figure, which were symmetrically bolted to the stub column. This beam ends were simply supported, and the stub column could move vertically. Therefore, an applied load on the center of the stub column generated a moment on the connection. The assembled specimen of Ostrander test stub are presented in this figure 1. The geometries of connection models. Ostrander's experiments include 24 test specimens of flash and plate connection. In this study, 7 specimens that are representing various types of configurations are accounted, and end plate thickness and stiffness of the column web are the main parameters to be focused. The geometries properties of the 7 connections which are analyzed in this study are presented in this tablet, the table 1. The material properties. Material is ASTM A36 steel is used for beam, column, and plate of the connection. The yield, stress, and ultimate strength of the connection were taken from the mean value of coupon test result, as you see in table 2. The bolt yield and ultimate strength are assumed based on the nominal properties of R325 bolt. The effective material properties are shown in the table 2. Finite element modeling. The three-dimensional finite element model are used to generate the effective moment rotation response of the connection. Geometric details of all components that are used in flash and plate connections are as same as those of the tested specimens given in the table 1. Due to the symmetry of the geometric details, loading and boundary conditions, only connection on one side that cruciform arrangement was modeled to reduce the computing time. The hexagonal solid element C3D8 type with 8 node was used with reduced integration and hourglass control as element type. The mesh density was increased in the critical zones of the connection. The contact area including bolt head and nut, 2 components were modeled by implementing the penalty contact algorithm with finite sliding scheme. The normal behavior that appears between two surfaces is defined as hard contact, and the coefficient of the friction was taken as 0.33 in the tangential direction. Boundary conditions and applied loads. The boundary conditions defined on the model realistically reflect the experimental step. In order to disallow the local deformation under the concentrated force, the column top force is coupled through the coupling constant to the load application point. The ball pretension load is applied as the first load case, and for this purpose, a thermal gradient is applied on the ball shank to yield equivalent pretension force yields. A force of 133 kilonewton is applied to the 90.1 mm diameters of bolt. The 50 mm vertical displacement is applied on the nodes of the load application point. The resulting moment or relative rotation of the connection are evaluated from equations 1 and 2. The moment is evaluated from equation 1, and the rotation is evaluated from equation 2. Where M is the applied moment, P is the summation of the reaction of the applied displacement on the beam, L is the beam length, R is the rotation, and D1 and D2 are the top and bottom flange horizontal displacement respectively. After analyzing the flash and plate beam to column connection, the deformed shape of connection are plotted and behavior is evaluated. This figure is show the deformed shape of the test, the number 11 and 0.03 radian rotation. The finite element analysis result of the flash and plate to beam to column connections. The results of the 7 specimens showed comparing with the experiment data and practical mathematical models. This is the result of test 1 model, the result of test 3, the moment rotation response of test 4, the test 6 result, the result of test 7, the test 8, and finally the result of the test 11 model. Effect of bolt pretension load. Now it's possible to extend the study of the connection beyond the experimental data having the prediction capability of the proposed modeling approach. The model is used to study the effect of bolt pretension on the response of the flash and plate beam to column connection. A variation on the pretension loss is modeled in order to monitor the effect of pretension. The test 1 and test 3 of the Ostrander are accounted, and varying value of pretension is applied. The variation of the pretension is limited with 100% is equal to 133 kilonewton, 75% is equal to 100 kilonewton, 50% 66.5 kilonewton, and 25% is equal to 33.25 kilonewton. And analysis result of the test 1 and test 3 with variation pretension load is shown in this figure 5 and figure 6. Figure 5 shows the moment rotation response of test 1 connections with varying bolt pretension. Here you can see that the pretensions in 100%, 75%, 50, and 25%. Sorry, this is also, here is a mistake. I put here the test 1 result also. I have a graph for test 3. Here's a mistake. This 2 graph is same. Sorry for that. And conclusion. In this study, the moment rotation behavior of bolted flash and plate connections are investigated by using three-dimensional finite element model and a practical mathematical model. The numerical analysis results are compared with the test result of a reference study from the literature. Analysis results show that the finite element analysis and mathematical model has a good agreement with the test data of the reference study. On the other hand, the effect of both pretension load on the response of flash and pellet connection is focused. The finite element analysis result reveal that pretension loads have significant effect on moment rotation curve of flash and pellet type of the connections. Thank you for listening. Do you have any question?
Okay, thank you, Mr. Ehsan. Do we have any questions from the audience? Well, thank you again. It was a very nice presentation and nice study. Are you about to finish your study or you're in the middle of it?
My study is, no, I'm not, I didn't finish yet. My study is maybe finished in this semester. This topic is a part of my study.
Ah, okay. Mm-hmm. Will you do any more analysis, or did you finish your analysis?
Yeah, I have a more analysis.
Mm-hmm. About what? You checked with the pretensioning of the bolts. What else will you try?
My analysis about this semi-rigid connections, the pretensions also, the bolt remove.
Okay.
Bolts forget it. Also, putting the results on frame analysis, something like this.
Okay. Okay. Thank you very much. I wish you good luck in your studies.
Thank you so much.
Okay. So we can move on to our next presentation. Ms. Alui will present this one. Actually, I had the chance to work with her in her master's studies about the bending behavior of hybrid fiber reinforced concrete beams. Sarah, if you can start your presentation. If you can again introduce yourself with a couple of words, that would be nice.
Thank you, everyone. Thank you. I am Sarah Alvi. I'm graduated from İzmir Yüksek Technology from the master degree of the Civil Engineering Department. First of all, I want to thank everyone for this good organization for this event. And I am ready to present my project.
Okay, please go on.
Mm-hmm. Are you able to see my screen?
Yes, we can see your screen.
My presentation is by the name of Bending Behavior of Hybrid Fiber Reinforced Concrete Beams. This presentation contains introduction and literature review, experimental work, result and discussion, and it will be ended by a conclusion. The bending behavior, the bending tests are one of the most common type of tests that are employed for investigating the efficacy of the fibers. 3-bond bending test or 4-bond bending test are the most common tests performed for research in this area. The objective in this study is to improve our knowledge on the use of hybrid reinforced concrete beams, where steel and polypropylene alcohol, named as PPA fibers, are used in the same mix under 3 and under 4-bond bending tests, as well as to obtain the effect of fiber hybridization on the bending behavior. In the literature review parts, 2 articles will be presented. The first one done by Zheng at 2019, where specimens with the usage of PVA, they were tested under 4-bond bending test with a different volumetric ratio, from where we could conclude that the PVA fibers can improve the flexure strength of concrete, and the PVA fibers can decrease the crack propagation. The second one is done by Sagiano at 2016, where a high amount of steel fibers in the mix was concluded that it's more adventurous, As well as we could conclude that a high amount of polypropylene can result in a general reduction in strength and toughness. Now I'm passing to the experimental work. During this project, we casted a number of beams and in the laboratory where the concrete mix content have mainly the Portland cement, class F fly ash, and 2 types of aggregates, in addition to a superplasticizer. As a reinforcement, 2 types of fiber they were used. The first one, that is steel fibers, that we used 3 types of it. It's shown in the figure 4, and the PVA fibers that is shown in the figure 5. To obtain the best results, 9 specimens they were casted, named as SA1, SA2, SA3, and SA4. For each of them, 2 specimens they were casted. The first one that it contains just steel fibers, and the second one it contains both steel fibers and PVA. The last one is named as plain. It does not contain neither steel fibers nor PVA. It's done just for the controlling part. This table can show us more specification of the specimens. For SA1, SA2, and SA4, the steel fibers content is equal to 0.75%. But for the specimen SA4, it have a higher steel fiber content equal to 1.25%. But the PVA fibers, it's stable for all of them as 0.25%. To obtain the best results, 3 tests that were executed in the laboratory. The first one is a 3-port Banting test, where the beams executed that have the dimension of 2.5 length, 0.5 width, and 0.05 high, where the specimen they were simply supported conditions, as it's shown in the figure 6. As well, a load was applied by a displacement controlled hydraulic actor at the mid-span, where up to steel cylinder that form a linear load distributed. 12 linear resistive position transits, they were attached at the bottom of the specimen, where a load cell also it was applied under the loading head of the hydraulic junc to measure the applied load. The distribution of the linear resistive is shown in the figure 5, where both of them they were placed at the middle, named as SA1 and SA2. It's more clearly in the figure 8. During this experimental work, the crack opening was also observed manually with the use of a digital movement gauge, where for that we could place metal beads distributed as is shown in the figure 11. The second test is the 4-point Banting test, where that is done after the first test. The beams that is cracked at the mid-span, it was cutted, and the half that it does not see the big damage, it was tested again. And the 4th Banting test with the usage of a rigid beam, as we can see in here. For this case, just 2 linear resistive position transgress where that's placed at the mid-span, named as P1 and P2. As well, for the first test, we observed the crack opening by placing the metallic beads. The third test is the compressive stress. The test that is for each mix design, we tested 3 cylinders with the usage of digital compression machine. From where we got this graph, that we can see that that there is a slight improvement on the compressive strength of the specimen after adding the steel fibers and after adding the PVA. Those are the photos of the specimen after the casting, the first test. Now we are passing to the result and discussion part. Here we can see that for the first specimen SA1, here with the specimen with the usage of PVA have a less maximum load comparing with the specimen with the steel fibers. Here we can say that the addition of PVA have an adverse effect for the short steel fibers. The second one, SA2, also here we can see that the load it dropped for the specimen with the usage of steel fibers and then it rises again. Here we can see the difference between the maximum load for the both specimens. We can say that the addition of PVA have an adverse effect for this mix. The third one, also we can see that the specimen with PVA have a less maximum load. We can say that the addition of PVA have an adverse effect for this mix. The fourth one, that is SA4, that is have a higher content of steel fibers. We can see here the big difference between the maximum load and the maximum moment between the two specimens. Here we can say that the addition of PVA have a serious adverse effect for this mix. From where we could obtain this graphic, we can see here the SA4, the last specimen, have the highest maximum load and maximum moment comparing to the other specimens. Also, if we continue the observation of this table, here we can say that also SA3 also as well, it have a maximum load high comparing to the others. We can say that the better anchorage is provided by double hooked ended that increases by bending capacity of this specimen as well. But for the shorter fibers, it can adversely affect the strength. But generally, we can see from this table that the addition of PVA have a negative effect in all specimens in distributed. It distributes the homogeneity of the mix. This is due that the fibers they're collected around the double hooked ended. Now we are passing to the 4-point bending test. For the SA1, here we can say the specimen with PVA have a high maximum load and maximum capacity. We can see that the PVA have a positive effect for this type of specimen. For the second one, they have a very nearby maximum load. So we can say that the addition of PVA have a neutral effect for this type of steel fibers. For the third one, the specimen with PVA have a higher maximum load. We can say that the addition of PVA have a positive effect. For the fourth one, that is contain more steel fibers, here we can say the addition of PVA have had a serious adverse effect. So the addition of PVA, it's not a positive thing, a positive addition for this specimen. If we can look at this figure, as well, we can see the specimen S4 have the highest maximum load and maximum moment. From where we can see also from the table that for this type of test, that is the 4-point bending test, the addition of PVA have a positive effect for all the specimens besides the SA4 because it contains more steel fibers content. Here, if we can look for this graphic, the maximum moment for steel fibers only specimen, that the specimen contains just steel fibers. If you compare the 3-point bending test and 4-point bending test, they have a very nearby results, but it's still the specimen with addition of under 4-point bending test, it have a higher maximum moment. But if we can look at the maximum moment for specimen with the usage of PVA and the 3-point bending test and under 4-point bending test, here we can say the specimen with the 4-point bending test, it have the highest maximum moment comparing to the other. But generally we can say for in 3-point bending test, the maximum moment it was at midspan, which caused the localization in the cracking. But for the 4-point bending test, the maximum moment it acts over a region at the middle, which causes several minor cracking along with a major crack. Now I'm passing to the conclusion. The steel fibers geometry, the type and ratio are the principal factor that it affect the level of load of the specimen. Like we can see in here, like the short steel fibers, they have the less maximum capacities. But for the specimen with the long steel fibers, they have a higher maximum load. Also the type, so specimen with a double hooked ended, it have a higher maximum capacity, or the ratio. So if we can see that specimen SA4, that it have a higher they have a higher amount of steel fibers, it have a higher maximum capacities. But we can see in here for the 3-point bending test, it have the addition of PV have an adverse effect. It always dropping the maximum capacity of the specimen. But for the 4-point bending test, it have the addition of PV have a positive or natural effect, with the exception of the specimen with the higher steel fibers content, that is the SA4. But generally, we can say that the benefits of hybrids fiber reinforced concrete are not unconditional. The fiber addition can disturb the homogeneity of the mixed design mainly. Those are the references that I used during this presentation. Thank you for your time, and I am ready for any questions. Thank you very much.
Thank you, Ms. Oloui. Do we have any questions from the audience? Okay, if you don't have any questions, again, thank you very much for this nice presentation. And also, it was a pleasure to work with you in this thesis.
Yes,
so we can move on to our next presentation. I believe, yeah, he's here. So our next presentation is by İbrahim Serkan Mısır and Prost İverden Balenda Bakala. I believe Mr. Bakala will present this study about the numerical modeling of behavior of reinforced concrete frames under biaxial cyclic loading using Diana finite element analysis. Mr. Bakala, before you begin presentation, again, I will, if you can introduce yourself with a couple of words, that will be nice, and then you may start your presentation.
Okay. Thank you very much for the speech that you gave to me. So, as you said before, my name is Prost İverden Balenda Bakala. I am a PhD candidate in the University, and today I'm going to present a few work that I did on with Diana finite element analysis, and so the work have been done before by Serkan and the others. So I use their data to make it possible. That's going to be the work I'm going to present. Thank you.
Okay, thank you. So you may start your presentation.
Okay, thank you again. So the work that I'm going to present here is named by the numerical modeling of behavior of reinforced concrete frame and the Biaxial cyclic load using Diana finite element analysis. First of all, we're going to introduce some concepts and present the methodology that we use to conduct this work. And from there, we're going to also present the experimental study that have been done before. And then we're going to use the data from this experimental study and make it in finite element model with dynamic. And then we're going to compare both experimental and numerical results. As we say, the importance of nonlinear biaxial model applicable to the analysis reinforced concrete frame have been done by many researchers and have been proved the importance in a seismic region. So for that, reinforced concrete frame are usually subject to combination of axial and lateral action, as the radius cause lateral deflection that in turn affect the horizontal stiffness. So that's gonna be our need to simulate the nonlinear behavior of the reinforced concrete frame due to the material nonlinearity. Also, the need will be to model the behavior of the interaction between frame and reinforcement. So as we can say, for the scope of this study is to assess the efficiency of a finite element model as a numerical tool to simulate the inferior reinforced concrete frame in plane behavior. So the methodology will be to select an experimental case study for verification purpose. Also, we're going to review all the literature regarding to experimental and analytic study. Also, we're going to take a look at DINA manual, and then we're going to create the geometry. We depend on dimension of concrete member like beam, column, and foundation based on literature review. Also, reinforcement bar and cross section. Also, boundary constraint. In DINA, similar as possible to experimental cases. And a suitable numerical conceptual model of each component of infill reinforced concrete frame will identify like concrete and reinforcement. And then the selection of the required parameter for the constitutive model of each component, like for concrete and reinforcement. Also, at the end, the application of the load in the model in order to simulate that of experimental case study. As the analysis that we're going to conduct, we will use a structured nonlinear analysis for how we work. Also, the efficiency of the simulation model was assessed using a comparison of experimental result from case study structure to the numerical obtained from the structural analysis. And then some of there is also another data that we use to get the reasonable result between numerical and experimental. The data was has been taken by from literature, also from DINA manuals. So in experimental cases, the tests were dimensioned and detailed as one base single story frame, and the beam section were constructed with slat to take into account the diagram actions. So here is the geometry of inferior concrete frame. So there is a dimension of beam, also of column and foundations. For the dimension of column is of 40 centimeter times 25 centimeters. For beam is taken like 40 centimeter times 25 centimeters. And for foundation, you have 60 centimeter times 45 centimeters. So we can, in this picture, it is this one part. So it's like a symmetric axis, as it is specified here. And in this case, the grade for concrete is 25 for compressive strength, and for reinforcement is taken for 420. And for displacement control, the nominal peak displacement level we consider, as we mentioned here, based on this diagram. And has a result for experimental, the first flexure crack on column was appeared at drift ratio of 0.20, which corresponds to 85.4 kilonewton. It's the same for the beam. Normally here is the beam. There is a row. It's for beam. And first yielding of longitudinal reinforcement in frame member occur at 0.35, which correspond to 117.3. And the observed maximum top load occur at 2.75, which correspond to 243.5 kilonewton. And the reach maximum drift ratio at 4.09, which corresponds to 209.3 kilonewton. So these results will be compared with our model that will be conducted with Dyna. So here is excuse me, there is some point missing here. Yes. So this is a load displacement curve for experimental with the result. And for finite element model Dyna, we take the dimension of experimental, and we define a foundation. We define a column, also a beam. And there is something very interesting here. We include a slider or a permanent load in Dyna. So the beam is simulated as rectangular beam, and slab is incorporated as permanent load. Has unit with Newton, millimeter, and kilogram. So the geometric definition is the same with the experimental case study. As boundary condition, XY transitional base was constrained. So the type of element, we got two elements, concrete and steel, so reinforcement. And for concrete, the concrete will be modeled as it is mentioned in Dyna manual, using plane strength elements, and width for beam and column is 250 millimeters. And for foundation, 600 millimeters. For reinforcement, we take two node bar elements embedded in plane stress element. And the cross-section area of bar posterior is 8, which corresponds to 50 meters square, and 40, which correspond to 150 millimeters square. Here we can see in this picture. For mesh, we take a square mesh and define a 50 millimeter for the plane stress elements. So the size of mesh, and the method was taken like a quadratic. That is defined in a dynamic. You can see in the picture on our right here. So we have a beam and 2 columns, and also for steel, and for shape. And the mesh type, we take exact quadratic. For constitutive low material model, we define for concrete total strength crack model. This model describes well the propagation of crack for material. And for reinforcement, we use Meneghetto-Pinto model that show good agreement for cyclic curve. Here we define all parameters for total strength crack. That's described the concrete, modulus of elasticity, Poisson ratio, mass density. For crack orientation, we take rotating. For crack bandwidth, we use the literature for rods. For tensile group, we use fiber model concrete structure code, and the tensile strength is defined. And for compressive curve, to find a hysteretic curve, we use Maekawa crack concrete curve. Also, we define the compressive, which is 25 megapascal. So here we have illustrate the parameters of dynamo.
Mr. Bakala, we are running out of time, so if you can come to your results maybe in a few minutes.
Yeah, I'm coming. This is for reinforcement for Meneghetto-Pinto, all the parameters. And here we define a steel plate here. And for cyclic loading, the nominal peak displacement was taken the same with experimental. And you see how we define the constraint load and place described. And as a result, we get the load displacement curve. And in this figure, we see for the push, there is pull and push. So push is more stiff than pull in our cases. And also, if there is good initiative stiffness. And of talking about crack pattern, we get the drift ratio at 0.20%, we get 107.27 kilometer. And at drift ratio of 0.35, we get 113.97 kilonewton. At the drift ratio of 2.75, we get 190.65 kilonewton. And the last one, we get 198.45 kilonewton. So we can compare here the table at the drift of 0. It's quite, there is not a big difference in terms of loads. And also for the first building here, there is not a big difference here, as you can see in all values. So if we based on this value, the result matching with our experimental campaign. So in the term of low descent, we can well see that the simulated force displacement curve and crack pattern show good agreement with the experimental result. So the blue one is for Dana and the yellow is correspond to experimental. So numerical simulation and experimental result of infill reinforced concrete frame have been compared with good correlation in terms of initial stiffness, ultimate stiffness, maximum force, and crack pattern. So for future work, the calibrated model of inferior reinforced concrete frame will be used to perform numerical experiment through a parameter study to investigate the influence of the mechanical property of infill wall in the strength, stiffness, lateral capacity. Thank you for watching.
Okay, thank you very much, Mr. Bakala. Do we have any questions from the audience? Okay, thank you very much again for this nice presentation. Are you about to finish your work, or at what stage are you in your work?
Yeah, now I finished with infill reinforced concrete frame, as I said. So the next will be to incorporate both infill reinforced and the masonry. So for masonry, I will take two types of wall, the standard brick and log brick.
Yeah.
So I will make the comparison between standard brick and the log brick. So the log brick is for my PhD thesis.
Okay, so you will model the infill wall too, right?
Yes.
Okay. Okay. Good luck in your studies. Thank you very much for your presentation. And so our last presentation is will be from Mr. Halim. Is he with us today? Okay, I guess our last presenter is not here with us today. So it means that actually we finished all our presentations for these sessions. For this session, I would like to thank you again for all the participants, and also I would like to thank all the people who put an effort to realize this nice conference. So thank you very much, and I wish you luck in your in your studies, and hope to see you again in other organizations like that. So thank you very much for all, and this concludes our session. Tamam değil mi arkadaşlar? Burada o zaman şey yapıyoruz. Çıkabiliriz. Herkese çok teşekkürler. O zaman tekrar.
Teşekkürler hocam.
Teşekkürler. Kolay gelsin size. Sağ olun.
Teşekkürler.